Ave Coders, and welcome to the complete tutorial on Numpy. First of all, I'd like to say that this tutorial was inspired by the work of Charles Kelly, so credits to him. Anyway, after completing this tutorial, you'll gain an in-depth knowledge of Numpy or Numpy, call it as you like. So we're here in Jupyter Notebook. First of all, what we need to do is we need to import this library. So I'm typing import numpy and then I'm specifying the alias, so we won't need to write numpy all the time, so np is an alias. And first of all, let's print what kind of a version of this library we have just imported. So I'm typing print np version and I've got 1.18.5. yours might be different, but I'm sure that the main tricks will still work. So I've just declared a variable called myList, and here in square brackets, I'm gonna list the elements. The trick is that in all other languages, maybe not all, but still, this will be an array. But in Python, it is a list, and you can watch my video on Python for beginners to understand the difference. But long story short, we need to convert this list into an array. So in order to do that, I'm going to declare a new variable called myArrayFromList, and in here I'm going to use a method called np.array, and inside the brackets I'm going to place the variable myList. And if I'll decide to print myArrayFromList, you'll see a difference. First of all, you're going to see that next to myArrayFromList, the type will be specified as an array. So if I'll press enter, you'll see the same numbers, but now it tells us this is an array. And of course, array comes with all sorts of features not applicable to a list. So I'm going to copy and paste it here, and I'm going to multiply it by 10. So what's going to happen? Every element of our array will be multiplied by 10. And this is a nice feature of an array that we can use later on. All right, so what if we'll decide to have a tuple? So in here, I declare a variable myTuple, and again, you can watch the difference between tuple, array, list, and so on in my video, Python for Beginners. And I populate this tuple with some random numbers. I don't use random generator because I have it in my head, but as you can see, the numbers are pretty different. As you can see, we have an integer, we have a negative floating point number, and we have an operation with some letter involved. So what's going to happen if I'll decide to convert it to an array with the same operation, np.array, and I supply my tuple as an argument. And thanks to the last element, which includes operation and this letter J, we have very non-trivial result. But if we'll decide to multiply our myTuple by a single number, let's say it's number 5, the behavior will be slightly different. As you can see, it just repeated this sequence of elements in the tuple 5 times. However, if we'll convert that tuple into an array and multiply it by 5, we'll get all elements multiplied by 5. So it will try hard to interpret those numbers with J and multiply them as well in its own interpretation. Now, in order to clear the screen, I'm going to use the revert to checkpoint. And if you don't know how it works, please watch my video on Jupyter Notebook. So now, because we have no imports, we'll need to import Numpy again, and I believe it is a good point to save here so that we won't need to import it every time we clear screen. So let's create a new array with the built-in function np.arrange, and we supply 10 as an argument. That means we're going to have 10 elements. However, I believe I've misspelled the word arrange, so it's just one R, and yes, that's true. So I'm going to rerun it again, and as you can see, we have 10 elements from 0 to 9. So as you can see, our array starts from 0, and ends with 9. But we can also create arrays and specify at which number we want an array to start. Let's say I'll use the same function and b.arrange with a single r, and I want it to start at 10 and finish not reaching 21. So this time we have 11 elements starting from 10 and finishing at 20. We can check the length of our array by using the function called len, and we supply our array as an argument, and as you can see, the length is equal to 11 elements in the array. So the first parameter in NP arrange is where we start our array. The second one is where we stop. But if we'll supply a third parameter, this will mean step, start, stop, step. So it means elements will grow by 2, not by 1. So 10, 12, 14, 16, 18, 20, rather than 10, 11, and so on. All right, so the next function we're going to be looking at is called Linspace. Linspace returns evenly spaced numbers over a specified interval. You can check out the documentation to see what it does. But basically what it does, if we'll give it a bunch of numbers and specify the start and the finish of a range, it will evenly space those numbers, those elements within that range. So let's see how it works. But first of all, let's do a markdown. If you don't know how to do markdowns, please watch my video on Jupyter. So 3 hashes and Linspace. This improves readability of your notebook, especially if someone else will be reading what you wrote or you're going to be revisiting after some time. And here we can even add a short description of what Linspace is or what it does. So let's begin with the function. So once again, we're going to define np.linspace and we're going to supply 3 arguments. The start of the range, the end of the range, and the number of elements we want evenly spaced. So let's imagine we need to put, say, 11 plates on a 30-meter table. So if we'll use a 3-meter interval between them, that should work pretty well. By the way, if we want to find out the number of elements in our array, we can always use a subfunction called size that should print 11. So this is really straightforward example, and we can clearly see that the interval between elements is equal to 3. But in case it is complex or long, or you can't be bothered to count, you can always use another parameter to the Linspace. So if we'll supply another 4th parameter, so let's say I declare this variable, my Linspace is equal to our np.linspace, and if I will supply a 4th parameter called red step and set it to true, it will return the size of the interval. I'll call my Linspace to print the result. And here we go. We have our array appended with the size of the interval. In our case, it is equal to 3. And in essence, our variable myLinspace consists of 2 elements. The first element is the array itself, and the second element specifies the size of the interval. Therefore, we can access those elements by their indices. So if I'll type something like myLinspace and inside the square brackets the element 1, so element 0 is the array and element 1 is the size of the interval, which is an element number 2. So Linspace is quite useful function, but what if we want to create an array and fill it with some dummy values? Let's say fill it with zeros. Coincidentally, Numpy library has got an answer to that as well, which is a function np.zeros. So if we'll specify 10 as an argument, we'll get an array of 10 elements, each of which will be equal to 0. So this type of array initialization is popular in, let's say, useful in linear algebra, in machine learning and data science. And we can also fill the array with, say, ones. This might be useful if we want to add an extra dimension or make two arrays match each other dimension wise. So the principle is pretty much the same. It just says np.ones. And these types of arrays can be not only linear. So let's say we want to have an array. Let's say we want to have an array of 10 rows and 5 columns. And in this case, don't forget that we must put another set of brackets. Otherwise, it will cause an error, like in this case. So let's see what we've got. So as you can see here, indeed, it consists of 10 rows and 5 columns filled with zeros. But we can also create an array of arrays so that we'll have 10 elements, each of which will be an array in its turn. And we can do that just by adding the third argument, the third dimension. And here, as you can see, it's 10 arrays, 5 rows and 3 columns each, and they're all filled with zeros. But we can also specify the type of elements we want to populate our array with. So let's say we use np zeros again. So we want 11 elements, each of which will be of type string. So in this case, it is not filled with zeros anymore, but filled with empty strings. We can also explicitly define the numerical type. Let's say we're going to put dtype equals int64. And now we can see that all elements are zeros, but without a floating point. All right, let's move on. And this time we're going to work with vectors. So a vector in essence is a one-dimensional array. So if I'll specify in here something like Ave vector as my variable, and in this variable I'm going to store the one-dimensional array. So I'm calling the function np.array, and it will be populated with random numbers that come from my random generator in my head. So 4, 8, 15, 16, 23, 42. So let's make sure this is an array indeed. So we're going to print the Ave vector variable, and we can see the type specified is an array. And now we can begin to manipulate it. But first of all, let's recall the basics. So if we'll want to access the element of index 1, we specify the index inside the square brackets. Array starts with 0, so indeed the first index or second element is 8. So -1 is the first element from the end. And if we'd say we want to access the third element from the end, we're gonna put -3, and indeed 1, 2, 3 is 16. So if we count elements from the end, we don't start with 0, we start with 1. We can also assign new values to the elements of our array. Let's say an element of index 1 equals 14, and now we'll see that 8 was swapped and it is now equal to 14. So array allows us to do that. Let's move on. Arrays can be not only one-dimensional but multi-dimensional as well, and in most cases they're called matrices. So in here I declare a new variable Ave array, and is equal to the array of 35 elements starting from a 0. I can print it out to show you what I mean. Indeed, this is a one-dimensional array starting from 0 and ending on element which value is equal to 34. So how can we convert this one-dimensional array into a multi-dimensional array? we can use the function shape, and we'll make it consisting of 7 rows and 5 columns. So again, the same elements are now represented as multi-dimensional array. Or should we really call it a matrix? And now if we'll try to address something by the index, let's say index 1, what is going to be returned is not an element per se, it is a row. So row 1 that consists of 5 elements. And similarly, if we're going to put -1, we're going to get the first row from the end, or in other words, the last row. But let's say we want to access a specific element in that matrix, say the element whose value is equal to 27. That is an element of index 2 in the row of index 5. So we can do that by specifying the rows number followed by the columns number. So if I'll replace it with 5, so the row of index 5 and an element of index 2, I should get precisely that element whose value is equal to 27. And instead of specifying those numerical indices, we can also provide it with some variables that will have a numerical value assigned to them. So we here specified row equal to 5, column equal to 2, and we supply row and column instead of numbers, and we get the same result. All right, let's get back to our original array, and let's say this time we want to know which elements of this array can be divided by 2 without a remainder. And to make it happen, we're going to use the modulus operator. So this code says something like, if after the division by 2 the remainder is equal to 0, then print true, otherwise print false. And as we can see, the first 2 elements can be divided by 2 without remainder, therefore we can see true. 15 divided by 2 will have a remainder, therefore it false, and so on and so forth. And let's say we can declare a new variable that could be populated with elements that could be divided by 2 without a remainder. So I'm declaring a new variable subarray, and in here I will use Ave array with this 0 mod 2 mask. And if I'll print it now, we see that it only consists of elements that can be divided by 2 without a remainder. In other words, we just wrote a very simple filter. We can take it further and we can present another condition. So let's say our subarray variable from now on will only hold those elements that from the previous expression they can be divided by 2 without remainder, and they are bigger than 10. So we only have 2 of them. All right, so let's roll back a little bit. I can press escape and DD. That will delete the fields. And let's say we only want those elements that could be divided by 4 without a remainder. So I will declare a new variable, 0 mod 4 mask. And I will use exactly the same construction, but this time after the modules operator, I'm typing 4. So if I'll print my variable now, we can see that we have pretty much the same result, because 4 in its own turn can be divided by 2, and all elements are pretty much greater than 4. And we could also combine these 2 filters with NP logical and we don't need any ampersands or and keywords, so we can just provide them as arguments to this function. And it returns the Boolean values for elements that could be divided by 4 and by 2. So in our case it's pretty straightforward, but you can try with say 2 and 3 or 2 and 5 and you'll get a different result. In fact, we can do it here and we'll declare another variable, and this time we're going to be checking the elements that could be divided without a remainder by 3. So to do that, I'll just type modulus operator and 3. And if I'll print my variable now, we'll see that the landscape has changed. So now we have false, false and true for 15, while in the first case it was false because it was not divisible by 2 without remainder, but it is divisible by 3 without remainder. Alright, so the next topic we're going to be touching on is called broadcasting, and it's a great excuse to stop the video and check it out in the documentation because it is an important, yet it is very straightforward concept, but it may take time to get your head around it. But in short, it allows array arithmetic between some arrays with a different shape or size. So let's say we will declare a new variable called Ave 3D array, and it will contain 70 elements. And down below, so I need to indent it properly, and say we don't want it to be a 1D array. As you can see, it's a 3D array. That is why we're going to use the shape function to shape it into 2 arrays, 7 rows by 5 columns each. So let's see what we've got. So indeed we have 2 arrays. It's 0 to 69. And indeed each array or matrix has got 7 rows and 5 columns. And now we can start with our manipulations in order to show you how this broadcasting works. So first of all, I want to do some simple arithmetics with our matrix. So I'll multiply it by 5 and I will deduct 10 from each element. And as you can see, each element was multiplied by 5 and 10 was taken out from that element. So next, let's say we want to create 2 matrices. One is going to be called left mat, and it will contain 6 elements, and this is going to be its shape. And the other, as you might guess, will be called right mat, and it will contain, let's say, 15 elements, and it will be of shape 3 rows and 5 columns. And let's say we want to multiply these 2 matrices. So in essence, we want to produce a dot product. In order to do that, I'm going to use the function from Numpy called dot, so np dot, and I'm going to pass our matrices as arguments. So multiply one matrix by another, and we get the final result. This matrix has got 2 rows and 5 columns, and it contains 10 elements. And once again, if you're going to go down the machine learning or data science path, you will going to use this operation np dot quite a lot. So what we're going to do, we will assign this dot product of these 2 matrices to a variable dot product. And I want to show you one interesting trait of Jupyter Notebook. So if I want to display all matrices and the result, so dot product, if I'll press Alt Enter, I will only get displayed the last variable, so dot product. Please bear that in mind. So I'll have to do left mat and right mat separately. So here is the left mat. This is an array of 3 rows, 3 columns and 2 rows, and right mat, 3 rows and 5 columns. And here is the dot product. So once again, the dot product is the result of multiplication of left mat and right mat. But let's get back to our original, our 3D array, and do some stuff with it. So if we want to know what is the shape of the array, we can always use the function shape. So it will give us that our array consists of actually 2 matrices, 7 rows by 5 columns each. And if you want to find out the cumulative sum of all elements inside this array, we can use the sum function. So as you can see, this is the sum of all elements in our array. But we can also pass a specific axis we want to sum our elements by as an argument. So if we want to sum elements by elements, so element wise, we can use the axis 0. So as you can see, the elements from the first matrix were summed with the elements in respective position in the second matrix. So in other words, 0 plus 35 equals 35, then 36 plus 1 is 37, and so on and so forth. And we can also pass axis equals 1 as an argument. And each element in this array consists of a sum of a column of these two arrays. So for instance, 105, this is the sum of all elements in the zeros column. So if we're going to use the same axis argument, but this time equals to 2, that will return the sum of all elements per row. So 10 is the cumulative sum of all elements in the 0th row. And now let's talk about the broadcasting rules. So first of all, we're going to create a new 2D array that I'm going to call Ave 2D array. And our new array will have 35 elements, each of which will be equal to 1. So I'm going to utilize the np.ones method, and the data type of those elements will be integer. And of course, we want it to look like a proper matrix. Therefore, we're going to use the method called reshape. So we want it to be 7 by 5, and we're going to multiply each element by 5. So as you can see, 1 multiplied by 5 equals 5. And here we go. We have a matrix filled with 35 elements, each of which is equal to 5 now. But what if we want to create a random value matrix? So we're going to declare a new variable, Ave random 2D array, and I'm going to use the function called random. So np.random.random, and I'll specify the size of 7 by 5. So it's going to create a matrix 7 by 5 and fill it in with random numbers in range from 0 to 1. And the data type by default is float. And so for the next trick, I'm going to use the function called setPrintOptions. So np.setPrintOptions. And in here, as an argument, I'm going to pass the value for precision. In this case, it's going to be equal to 4. So in essence, how many digits are going to be after the decimal point? And on the next line, I will multiply our matrices. So Ave 3D array will be multiplied by Ave 2D array. And let's see what is going to happen. And despite them being really two different matrices, we'll still have this result. So what's really happened is that Numpy has checked implicitly that these two arrays are compatible for multiplication and multiplied them. So let's create another array that is compatible with our Ave 3D array. Let's call it Ave Vector, and it's going to contain 5 elements multiplied by 7. So each element will be multiplied by 7. And let's assign a new value to the first element, so index 0, and the value will be -1. And let's see what happened. All right, so this is our Ave vector, and now we can do a division. So Ave vector is compatible with Ave 3D array on dimension 2. Therefore, we can do a division. We can divide Ave 3D array by Ave vector. If they would have had different dimensionality, we could probably get an error. But in this case, the broadcasting rule works, and we can see the results of the division. Alright, so let's move on to the next topic, and the next topic is called structured and record arrays. Alright, so the cool thing about structured arrays is that their data type is a composition of simpler data types organized as a sequence of named fields. Right, so let's create a new array. We'll call it employee data def, and in here we're going to specify the elements of the array. But this time the elements of the array will be tuples, and I'll show you what I mean. So imagine that first tuple will consist of the string and the data type. So the element itself is going to represent the name, and a data type will be a string with maximum length of 6. Next will be height with the floating point, and next one will be weight. Again, we're going to use the floating point here. And the last one will be age, and we will represent age as integer. So let's print our employee data def, and let's see, this is what we have. So nothing really special. However, we can use it as a framework for our next trick. So let's say we'll organize a new employees array, and it's gonna consist of zeros. So we're gonna have 4 zeros, and the data type will be equal to employee data def. So essentially that will mean that we have 4 placeholders currently set as 0, but their structure will resemble the structure of the elements in employee data def. So this is how it looks like. Currently it's all set to 0 or empty string, and essentially from here on we can start to populate our employees array with our employees. And we'll do that in the usual way. We'll access the element of the employees array by its index, and we will assign a new value. But this time it's not going to be a string or a number, it will be a tuple. So let's say an employee by the index 3, we'll call him Donatello, and he's going to have a height of, let's say, he's going to have a height of 2 meters. He's going to be 100 kilos in weight, and his age is 105 years. And let's do another one straight away. Let's say we want to assign some values to the employee number 1, therefore we use index 0. And this time the employee's name will be Raphael, and his height will be 198 centimeters and 96 kilos of weight and 106 years old. So let's print our employees array and see the changes. So I've used autocompletion, and here we go. We have Raphael and Donate, because we specified string to be maximum of 6 letters. Essentially the names were cut down to match that length. And as you can remember, we can also specify the range we want to have our array printed from. So in this case I'll specify 0 and a colon, and this is going to have essentially pretty much similar result. It's going to print the whole array. But if I'll change 0 to 1, let's say I'll copy and paste it here, and I'll change it to 1. So in here we're going to see that Raphael was not mentioned in the array result. And we can also specify that we want one particular type of elements being printed. So in this case we're going to assign them to the variable ages, and here we go. This is the representation of all ages of all employees mentioned in our array. Alright, so let's try to build something even more epic. So I'm going to declare a new variable called company employees all, and it's going to be a multi-dimensional array filled with zeros. So it will consist of 4 matrices of 3 rows by 2 columns each of the data type employee array. Or rather, the data type should be of the original array employee data def. And let's print and see what we've got. And basically, because we have so many dimensions, so in case we'll want to assign a new value to a specific element, we have to specify which matrix it is in, on which row, and in which column. So we'll do this inside of the square brackets, so 3, 2, 1. And again, we have to supply a tuple. So this time, let's say our employee's name will be Pippin, and his height will be 90 centimeters, his weight will be 120 kilos, and his age will be 98. Let's have a look. So as you can see, Pippin was added last in this matrix. And if we want to print all the heights of our employees, we'll just supply height in the square brackets, and as you can see, all of them are zeros apart from the last one, which is Pippin's height, 90 centimeters. Similarly, if we want to get results for, say, height and weight, we can put that in the square brackets, and as you can see, we'll get the height and weight. All right, let's move on. And for the next trick, we're going to declare a new variable. We're going to create a new array. We'll call it Ave array. Simple as that. And we're going to use the arrange function with the number of elements equal to 24. And we're going to put that in brackets because we want to reshape it straight away to be a 2 matrix 3 by 4 array. So this sort of trick when we put these functions together or methods together via the dot is called chaining. So as you can see here, our array consists of 2 matrices 3 by 4. And let's say we're going to declare another array, test Ave array, or better, trial Ave array, and it will represent our Ave array, but with a single value that is going to be appended to the Ave array, and we use the function append in order to do that. So in here in the brackets as an argument, we supply Ave array, and inside the square brackets we put the sequence of elements we want to append to our Ave array. I've said the single value going to be appended because we treat the sequence of elements as a single value in this argument to the append function. And as you can see now, it was literally flattened with the extra sequence added to the end of the original array. So we can reshape it again. We'll say we want it to be 7 by 4. And as you can see, this is the same representation, but this time it has 7 rows and 4 columns, but those values appended to the array are still there. All right, so let's do this trick again. This time I'm going to declare a new variable, new trial array, and I will make it equal to, I'll use a function array this time. And inside of this function as an argument, I'll pass the np arrange with 24 elements, and I will reshape, so I'll chain another function to it, which is reshape and I'll make it 2 by 3 by 4, and I will multiply it by 10, and I will add 5 to it. And this is the result we get. In the next example, I've already got result of the append operation, so I've appended new trial array to our Ave array using the axis 0. And now we essentially have 4 matrices, 3 by 4 each. But all elements from both matrices were preserved. So I'll copy and paste it here again. And this time I'm going to use the function shape, and we're going to see what the shape of this new array is like. And indeed, it resembles what we actually can see on our screen. But what will happen if we'll change axis to 1? In this case, we got 2 matrices of slightly different shape. As you can see, it is now 6 by 4 and 2 matrices rather than being 4 matrices 3 by 4. Let's check the shape scientifically. It's 2 matrices 6 by 4 indeed. If axis 0 and axis 1 is not for you, or it's a bit complex for the comprehension at the moment, Numpy has got a different functionality that is much easier to understand intuitively. So let's say we have an Ave stack variable, and we're going to use np hstack, so stack matrices horizontally, so on top of each other. And in here, as an argument, I'm going to give it a matrix 1, Ave array, and matrix 2, new trial array. Let's see what happens. Ave stack. And as you can see, they are stuck on top of each other, so we made a horizontal stack. And as you may guess, we also have something called the vertical stack. And we're going to use the function vstack. And we are back to 4 matrices 3 by 4. So the ability to manipulate the matrices is a very useful skill in machine learning, data science, and linear algebra itself. So let's move on. The next topic is how the insertion works in Numpy. So how we can insert elements into the matrix, we already know that, but how we can insert another matrix in another matrix, this is what we're going to look at. So we have Ave array, and this time we want to insert one new matrix into that Ave array, which is going to be filled with numbers 666. So to do that, we have one argument as Ave array. This is the array we want to perform insertion on. Then the element we want to insert, and axis is going to be 0. So let's see what we come up with. And as you can see, 1 in this case was an index, and as the element by index 1, it has inserted a new matrix filled with 666. Let's see what happens if we'll perform the same operation. We'll just change axis to 1. And as you can see, every row of index 1 in both matrices was changed to elements of value 666. Let's try and change it to, let's say, axis 2. And as you can see here, we have all columns of index 1, all elements in those columns changed to 666. All right, so now we know how to insert elements in multi-dimensional array, and let's have a look how we can delete elements and copy them. So first of all, I'm going to declare a new variable del array, And I'll use the function called empty, so np.empty. And if I'll pass the AveArray.shape as an argument, it will create an empty array that will have the same shape as AveArray has. So the next step, we're going to utilize the function copy2, and we're going to use this del array, the empty array, and we'll copy AveArray to our newly created array. And here we go, our del array that was initially empty now is populated with elements from AveArray. And if you want to delete one of the matrices in our del array, we're going to use the function delete, and we'll pass del array as the first argument. Second argument is the index of the element, and then the axis equals 0. So now we only have one matrix left in our del array. And if I'll pass 0, we'll see that the first matrix was deleted and the second matrix is presented. And if we'll change the axis from 0 to 1, it will delete the row of index 1 in both of these matrices. So let's do it. And as you can see, the row of index 1 was deleted. So now we have the row of index 0, and this is what's going to happen if we'll change the axis to 2. So the matrix is pretty much reshaped. All right, let's move on, and we will have a look how the concatenation works in Numpy. So here I've declared a variable called alpha, and I'm going to use the function array, and I'm going to populate it with some elements. So 1, 2, 3, 4. And the next step, I'm going to create another array called beta or beta that I will populate with some other arbitrary numbers. Let's say it's going to be just 5, 6. So it's essentially going to be a 1D array or vector. So long story short, concatenation is the action of linking things together in a series. So here is how our alpha array looks like, and here's our beta. So it's pretty straightforward, very easy to follow. And next step, I'm going to declare a new variable together, and I will use a new function called np concatenate. And as you may guess, as an argument, I'll pass alpha and beta. And of course, I'll need to specify the axis by which we're going to perform the concatenation. And here I'll print the result of together. And as you can see, concatenation by the axis 0 gives us essentially our arrays and vectors being stacked horizontally on top of each other, and the shape is now 3 by 2. And now I can assign a new value, say row index 1 and column index 1. I'm going to change the value to 666, and I'll print the together. Here we can see the 666, but we can also populate our arrays using loops. So if I'll create a new array, so in here I'll say arrays, I'm trying to distinguish it from the keyword array, and I will make it np0, so it's full of zeros of shape 5 by 3 by 4, and down below I'll use the standard for loop, so for n in range, and here I'll specify the first shape parameter of our array, 5, and in here I'll say that when we iterate, we'll change the value of each element we're going to iterate through to the number, random number. And let's print the arrays and see what we've got. And as you can see, the array is now fully populated with random numbers. So we've iterated or looped through this array, and we assigned a new random value to the elements of the array. Alright, so the next function we're going to look at is called stack. So here I'll declare a variable stack0 and I'll use the np stack, and I'll pass arrays as a first argument, and second argument is going to be axis 0. Below that, I'm going to declare a variable stack1 and I'll change the axis to 1. And similarly, below that, I'm going to declare a variable stack2 with axis 2. So what stack does, it joins a sequence of arrays along an axis. So I'm going to call it the variable stack0 to show you what I mean. So here's our stack0. So it is pretty much a copy of our arrays. And here's our stack1. The same elements, but just organized in a different shape. And stack2. Again, same elements, but organized differently in terms of shape. Alright, so now we know all sorts of joining elements in the array and joining arrays. So let's have a look how the splitting works. So the function split, I'm going to use the same arrays. So here I'll declare a variable before split, and let's say it is equal to the stack0. And if I'll print the shape, it's going to be exactly the same shape as stack0. Next, I'll declare a new variable called as0, and I'm going to use the function np.split, and as arguments I'll pass our before split, then 5 and axis 0. And we shall see that our S0 array now consists of 5 different arrays, but the elements all stay the same. And thanks to the useful functionality of Numpy, we can really see an array. As you can see, the type is next to the entity, if you like. So we have 5 arrays. Now let's try again. Let's declare a variable s1, and this time we're going to split our before split array into 3 arrays. So I'm going to pass before split as an argument, then 3, and I'm going to choose axis 1. And as you can see, we not only have 3 arrays, but the shape of array is slightly different. So in other words, the elements were arranged slightly differently between those arrays. Let's move on to the next topic. So I'll declare a new variable Ave start array, and again I'll use the function array, and in here I'll provide np range of size 24 as an argument, and let's print out Ave start array, and here we go. There's a flat array of 24 elements long. So if I'll print shape, we should see 24. So pretty standard 1D array. And now we can do our next trick. First, let's practice some reshaping. So I'll declare Ave 3.8 array, and I'll use our Ave start array. I'll use the function reshape, and let's say we want to make it 3 by, let's say 8. Bear in mind, 3 multiplied by 8 equals to 24, so we need to make sure our dimensions are compatible with the number of elements we have in an array. And as you can see, our array has been reorganized into 3 rows and 8 columns. And now we are ready to apply a new function called a ravel or ravel. So it returns a contiguous flattened array. So long story short, we'll take this Ave ravel array variable, and we'll assign a result of flattening the Ave38 array. To do that, I'll use this rabble function. I'm going to pass no arguments. And if I'll print the result, we'll see that this 3 by 8 array is again 1D array, so it has been flattened. But Numpy has also got a function called flat, which is in essence a 1D iterator over the array. The difference is that flat does not return an array, it returns an iterator. So let's create a simple for loop. Let's say for n in our array, our 3 by 8 array. And we'll call that flat function, and we'll print the result. We'll print each element separately as a sequence. All right, let's move on to the next topic, and we'll see how we can rearrange the elements in the array. I have prepared already a couple of arrays to save some time, and let's start with first array, Ave38 array. We've already seen it. So this is how it looks like. And this time we're going to use the function called fliplr that's going to flip the array in the left-right direction. So we pass our array as an argument, and we'll see that our elements in the array were flipped from right to left. So the very last element in the row in original array is now the first element, and so on and so forth. And let's see what's going to happen when we will apply our fliplr method or function to this array that consists of two matrices. So essentially what's going to happen, it will flip the whole rows in those matrices. Or you may look at it as it's flipping elements inside one particular column up and down, but at the same time it's really just flipping the rows altogether. And if you want to reach the similar effect in the array that only consists of sort of one matrix, like in here, so the previous array consisted of two matrices, this one is just one matrix. So we'll use the function called flipud, so flip up and down. So that will flip the rows essentially. It will put it head over heels, and here you can see the result. But if we'll apply this flipud to the array that consists of two matrices, it will essentially just swap these two matrices around. So the matrix 2 is now matrix 1, and matrix 1 is now matrix 2. But the elements inside those matrices are pretty much as where they are. And we can also roll array elements along a given axis, and for that we can use the function called roll. And when we do that, the elements that roll beyond the last position are reintroduced at the first. So let's see it in action. np.roll, and I'll pass our Ave start array as an argument. Let me rewrite that. So I'll have Ave start array. So this is so we can visually see how it used to look like. And now I'll use this np.roll. I'll pass this Ave start array as an argument. And we want to roll by 5 positions. So as you can see, 5 elements from the end of the array are now in the first 5 positions of this array. So once again, if we'll change it to, let's say, -5, we'll roll them backwards. So they are essentially been rolled in the other way. So first 5 elements are now last 5 elements of this array. Let's try this function on 2D array. So we'll use Ave234 array, and here we'll put 2. And as we can see, last 2 elements in the second matrix are now first 2 elements in the first matrix. And similarly, if we'll use -2, we'll see that first 2 elements of the array 1 of the matrix 1 are now last 2 elements of the matrix 2. And we can also rotate an array by 90 degrees in a plane specified by axis. So the rotation itself, its direction will be from the first towards the second axis. So here's our Ave 3.8 array, and here's the function np.rot90 with the argument Ave 3.8 array. And as you can see, now it is a reshaped array of 3 columns and 8 rows. Prior to that, it was 3 rows and 8 columns. So let's check a few more functions. The next one we're going to be looking at is called tile. So essentially we can give it a sequence of numbers and we can say how many times to repeat them, and it will populate the array with the result, which is the repeat of this sequence of numbers. So let's say we have an array, it consists of 10 elements. And again, just a small remark, there are loads of functions in Numpy. So here I'm only mentioning the most important ones. If I've missed something, please let me know in the description. But if I'll use all of them in this video, it's going to be as long as Game of Thrones, so I don't want that, and we're concentrating only on those that will most likely be used by you the most. So here we go, np tile, and as an argument I'm passing this array, so Ave array 1, and as a second argument I'm specifying how many times I want this sequence of numbers of all elements in that array to be repeated. So here we have a new array which consists of 5 repeats of this 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 thing. And we can also reshape it so it now looks much nicer, and now at least we can clearly see how many repeats of what we have in our new array. And again, we can modify this construction slightly. So I've declared Ave array 2, and I'm going to create an array of 7 elements. And here I'll use this tile function, but I'll use it slightly differently. So as the first argument, I'll pass this Ave array 2. But as a second argument, I'm going to pass a tuple 3, 1, which is something that is used for the replication. It is not recommended to do so, but there is a tool, there is a mechanics that can allow us to do this sort of reshaping from start. And as you can see, it was repeated 3 times and it has already got a shape of 3 by 7. We can also use a function called a repeat. The main difference is that it doesn't really replicates the elements, the sequence of elements, but it repeats certain elements the number of times we specify. So here we'll use np.repeat, again Ave array, let's say array 2, and as the second argument I'm going to pass how many times I want to repeat each element. And here is a result. Please give this video Emperor's thumbs up, toll the bell and subscribe. That was V. See you in the next lesson. Bye for now.